All right, we're going to get started with this week's seminar. Thanks everyone for being here, either in person or online, of course. We're enjoying the cookies and look forward to getting to share cookies with more people in the near future. So this is the second week of our seminar series, and this last week we got to hear from a bunch of faculty about all the fun stuff they've been doing recently, and this week we're going to hear about all the fun stuff our graduate students did over the summer, and with some of their some of the internships and summer programs that they participated in at the national labs. So we have, I believe, six presenters. We're going to try to keep it on schedule. So please, if you're presenting, keep it on schedule. And we'll start off with Arjun Earthperson is going to go first and talk about whatever this means.
Oh, yeah.
I don't know stuff. So
yep. Sounds good.
So
right.
The floor is yours.
Thank you. I just need to figure out a clicker for a second. So
yeah, just use the space bar.
Oh, okay, gotcha. Yeah, perfect. That simplifies things. All right. Hi, everybody. I'm Arjun. I'm a second year grad student and currently working on the reliability of autonomous control systems in the PRA group. So that's Dr. Diakonisa's lab. Over the summer, I was interning at INL as a continuation of the effort in this research space. And I know the title is like really wordy here. I mean, it's pretty long. Hopefully by the end of this presentation, you will have some understanding of what some of these terms mean. I have also tried my best to keep the definitions on every page because I get lost pretty quickly. And this thing is not doing the thing. Okay, there we go. So as I was saying, this is a continuation of the ongoing work. This is part of an LDRD with INL. This is part of the Fission battery initiative at INL. And so the objective is to develop a R&D method for successfully enabling the reliability calculations and modeling of autonomous control systems. And in addition to that, for adversary human action. So that's in the space of cybersecurity. Well, that's fine. And so, so a lot of terms here. We're looking at what a fission battery is. Essentially, INL defines a fission battery as a fission reactor with some other attributes, such as being economic, which is to say cost-effective and throughout the entire life cycle, standardized in the sense that it should be modular and should be able to link together with other things and deployed easily. And then installed, which means you can deploy it and just like forget about it. And of course, unattended, which means once you deploy it, you can just kind of walk away from it. So it could be in a container or something like that, and you just walk away from it. And this is moving by itself. And reliable, which means hopefully you don't have to come back to fix it. And so what is the motivation for doing this? Well, if you want to build anything, I mean, that's nuclear, you need to follow the licensing requirements, right? And the NEI 1804 document provides guidelines. So there's a non-light water reactor draft that is, well, that provides the guidelines. And so part of that is to perform a PRA, which is the probabilistic risk assessment for a fission battery. And when we do that, we want to make sure that we make realistic assumptions about our system. And so part of that is to model the control system reliability as it is. Since I said it's an autonomous system, it means that it's going to run on its own. There's going to be no human operator in the loop at any given point in time. Maybe apart from maybe installation and then end of life stuff. And so historically, this type of work has been done for, let's say, space applications by doing rigorous testing. And so that's true for, let's say, if you're sending out like a satellite or something in space. And in that case, you will do a lot of testing before you, send out your satellite or rover out in space. But oftentimes that's not possible and it's expensive. So we can do something else, which is simulation. And that's the core of this particular research. And so what we're simulating here is a fission reactor. This is from 2004. It's called SAFE 400, which is the Safe Affordable Fission Engine. And this was built by NASA, for NASA by Los Alamos. And it's used for propulsion, but it contains in it a 400 kilowatt. This is going to keep doing that, so sorry about that. So it's a reactor with control drums to moderate the fission rate. So as opposed to a typical reactor that you may have seen that has control rods, this thing has control drums, which means instead of moving linearly, it moves axially. And so as you can see on the diagram, there's some B4C, right? All right, so that's our system. But we want to be able to control the system. And so if we want to control the system, we need to come up with a control model. Always one step ahead. And so in this case, the plant is the control drum or set of control drums. In this case, it could have been 5 or 6 control drums. And we have a typical classical controller, which is a PID controller, which is a proportional integral derivative controller. And in this case, it's cascaded together with a high-level input which says, look, I have a reactivity target. I want my reactor to be at a certain reactivity at any given point in time. And I want to do that by mediating the control drum position. And so that's the first PID that you see. The equation here comes out of the work of Dr. Shannon Bragg-Sitton from, again, 2004. And so this model is built around that logic. And so we can go from reactivity to control drum position to the actual motor drive signal that moves the control drum in position. And so that's the system. Now we need to talk about what are we doing. Typically, a PID controller is not implemented as one thing on a computer, or on your autonomous control system. Typically, it's part of a PLC that's running hundreds of PID loops at any given point in time. And that's ultimately modeled as computer hardware. And so if you want to be able to capture failures at the controller level, we want to be able to look at, well, what's the code, what's the hardware, and how do those interactions happen? And so this is a typical pipeline that we have kind of seen over here. So you start with the source code. So that would typically be the logic diagram for, or the source code for a PID controller or a set of cascaded PID controllers that you compile into hardware-specific assembly instructions that's dependent on your machine. So that's, if you're running it on your home computer, it would be an x86 processor. So if you're running it on a Raspberry Pi, it would be an ARM processor. If you're running it on a PLC, it would be specific to the PLC's logic. And you compile that, and you can, and using this tool called LLVM parse, which is also part of the DEPM methodology, we create what is called the DEPM model. As an input, you also need, so it converts everything, all the assembly to failure models. And for each instruction at that assembly level, you provide a failure rate. So an addition operation, for example, may have a lower, I could argue, failure rate than a multiplication operation. Why? Because addition requires maybe orders of magnitude lesser number of transistors to implement than a multiply operation, but it depends on what is implementing it. So this is good because either as an analyst, you can provide this information, or if you have this information available from a manufacturer, that's already available to you. I mean, Texas Instruments builds billions of transistors, billions of CPUs that run for billions of hours. They have a very good understanding of how their systems fail in ambient or nominal conditions. And from that, you go to the DPM model, and I'm going to show you that next. So with all of that, what we get here is just one half of the DPM model. It's all the relationships between all the instructions. So if you don't look at assembly, don't worry about this. It's a lot of move operations. Move the data here, move the data there, etc. Anyway, it's there. I just wanted to show you that. And when all of this is done, oh, I should also mention, over here, we were only modeling the PID controller. There's also the entire control drum. We haven't modeled that. Modeling the control drum requires further analysis. You have to look at the physics of failure models. You have to look at the mechanisms by which it would fail. And so statically, we have performed some analysis here using a simple fault tree. This is done on an in-house tool that our lab is building. It's called OpenErrorPro. You can access it at openerrorpro.org. It's free to use, and if you want to develop software for us, that would be awesome. And so that's for the control drum side. And now we put everything together. So I haven't mentioned anything about EMRALD. EMRALD is tool that essentially performs dynamic event tree analysis. And we link DEPM to EMRALD, and we map it from the failure space to a function space. Meaning the cloud that you see in red is showing us that DEPM is mostly interested in the failures in the PID controller. And the failures there happen because they are affected by perhaps the ambient temperature, because computers or transistors or semiconductors are affected by temperature, and the flux in those areas. So if you can instrument your PID controllers appropriately, you can measure the flux, you can measure the temperature, and then on the fly, get a new failure probability for your PID controller. And as you saw, the system itself was pretty complex, so you can't like directly make that assumption. You have to run the model and get some results. One thing to mention here is that this is all based on discrete time Markov chains, which means it suffers from what is called state space explosion, which means you get too complex of code, and then now you're waiting until the end of the heat death of the universe and all of that. So you don't want to do that. But so there's some part there where you have to be careful as to how you design it. But what you get from EMRALD, all EMRALD asks is it asks questions in a very functional sense. It says, look, I want a target reactivity. What is the likelihood that I will get that target reactivity? And based on that, EMRALD will then decide how to branch next in its event tree. This is standard in PRA. So that's the model, and this is ongoing work. There's a lot going on right now. As I said, this is the first year. There's at least a couple more years of this work. We're going to continue doing that. And I've skipped a lot of slides, but here we are. Oh, so finally, I just wanted to mention all the people who are on this call. I think the team from INL is online and on the call, so I want to thank everybody. I want to thank Courtney and Steve and Troy and Thomas and Bree and Professor Diakonisa. And I also want to mention Daniel and Lakshita, who have been working on this project. They were interns at INL, they're undergrads here, and they're not here today, but they've been working a lot with interfacing the code and making sure that it all works. And to ask like how the virtual internship experience was, I mean, it was really fun because I was here over the summer and my entire lab just hung out. And that's kind of how it was. So thanks.
Any questions?
Yes, questions.
And we're between last week and this week, we're going to have to work on it.